Okay. All right, so let's get started. Let me get the lights and whatnot somewhat adjusted. I think today will be pretty straightforward. It won't be anything that's terribly complicated, but I want to walk you through some fundamental calcs associated with section properties and whatnot. This is stuff that I know you all have seen before, and I know if you had me for deformables in one way or another, we've done this before. But this is just to sort of get you back into this swing of things and get you more get you acclimated to this stuff that you're going to find, when you're researching bridge types and costs and systems and all of that. Okay, so week two, I have a typo here, should be week. I don't know what I was trying to say there. I'm just going to delete that. All right, so here's what we're going to do for meeting minutes. So this is week 2, and your meeting minutes are going to be due the following week. Now, usually they're going to be due on Wednesdays, okay? But this week I'm going to push that off until Friday, and the reason why is because I want to give you all a chance to ask questions about it in class if you need, and we're not going to be here on Monday. So Wednesday will come, we'll have class, and then you all will submit them on Friday. Now, this is what I am planning to do. I've never really set up teams and whatnot through Blackboard, so I'm not 100% sure how this is going to work. But if possible, what I'd like to do is set up teams or groups on Blackboard and assign the team leaders for each of your 2 companies, and then they'll be the ones that submit it, and you all won't have to worry about it. So let me see. So you are the leader of yours, and who's the other? Rachel. Okay. Okay. That helps out. So what I will try and do is I will try and set up the 2 companies, and then I will assign the leaders, and I think you can set it up to where the team leaders will just submit. If that doesn't work, I'll just have you email them. It's only 2 documents. I think I can keep track of that. But yeah, other than that, that'll be how we do that. Any questions about all that? Well, we could. Honestly, I think each individual team needs to do that. That's an idea. If it doesn't work, we might do something like that, or the server thing where you can. Did you all use the server for Computations? So we might do that. So we'll figure something out. Honestly, other than minutes, though, there aren't that many submittals. There's only your 3 reports and whatnot. There will be your team evaluations, which we are going to have 3 team evaluations that are done throughout this semester. And I didn't have it on the slide, but I'm actually, now that we're talking about it, it's a good idea I'm bringing it up. Your first team evaluation is not going to be worth very much on your grade, but it actually is going to happen somewhat soon. So your team evaluation will be it'll probably sometime in the next couple weeks. So the way that'll work is this. I have a spreadsheet that I've set up where you'll go in and you'll type in your name and you'll type in the names of your 3 teammates. And you will grade your teammates on a scale of 1 to 5 on a series of categories. Now look, I understand it's like week 2 and we haven't really done anything yet. So that's why this rating is not going to be worth much. But you'll do one for your alternatives phase and one for your final phase, where you all will really have a better idea in terms of, is this person contributing or not? And that does affect your grade. So it gives you all an intrinsic motivation to be participating in your company's efforts. If you're the one who's just saying, I'll just let them take care of it, that's fine. And then when your team evaluations are coming in, they're going to reflect that, and that's going to affect things. So just, it's just something to keep in mind. Any questions about all that? Okay. So today what I want to do is I want to go through some example calcs. I'm going to set up a spreadsheet to do some fundamental section property stuff. Again, the reason why I'm focusing on steel is because with concrete you can look them up. There's no calculations really that need to be performed. But I'll say this. regardless of if you're dealing with a steel bridge or a concrete bridge, there are still some additional calculations that'll need to be done. And what I show you today will help you with that. This is sort of the first step, because given a set of bridge dimensions, you need to be able to compute things like moments of inertia and section moduli and what have you, because those are going to be the first steps in determining stresses. And if you can determine stresses, you can determine whether or not that girder is safe to resist those loads. And if it's unsafe, then you need to bump it up. If it's too safe, or if it's... But once you've got a size, then you can get into scheduling, cost estimates, management situations, and what have you. Make sense? So again, I just want you to see the whole picture. Okay. So let's take a look at this. So this is the bridge that I'm going to look at, and I'm going to write just some data right here on the board. I'll replicate it on the Excel sheet. So let's just take a look at this. All right. So first off, what's my girder spacing? 10 feet. Okay. Now right off the bat, I'm going to say that's 120 inches, because one of the things that you will see in these calculations is that it's usually better to reference everything in a consistent unit. So I'm going to just go with kips and inches. That's typically what I'm going to do throughout the semester. So let's see. The overhang, what's the overhang? 3'6", right? So 3. Okay. All right. Now let's take a look at the slab thickness. Okay. Now what I'm going to say is this. I'm going to say that the total slab thickness is 8.5 inches. Okay. But actually, 8.5 inches. But half of it is going to wear away over time due to use, general wearing, ice trucks, scraping the deck over and over. So we're going to have half of that slab wear away. So I propose that the structural thickness of that slab is 8 inches. Okay, does that make sense? So when we look at strength calcs, trying to compute stresses or moments of inertia or resistance, PMN, stuff like that, we're going to use this. But when we look at loads, okay, loads are the forces that are being applied to the bridge, we're going to look at this. And that may not seem like a lot, but imagine how heavy the entire bridge. It's not feathers. That's a fair amount of load, so it's something you need to consider. Yes.
How do you account for the haunches? You're saying it's not that much, but it's still there.
That's a good question. I'll say this, from a load standpoint, you do need to account for it. You actually do have to account for that little bit of weight of material. From a resistance standpoint, we typically just neglect it. When we look at our when we look at our section properties, like our composite section properties, and we'll draw this on the screen so everybody sees it, we typically just say, our section looks like this. Now, there are some jurisdictions that actually do count on that little bit of concrete right there, like when they're computing moments of inertia. I don't think you can really count on it. So that's just me. The question was, how do you account for the haunch? You were talking about this little fillet of concrete right there. From a load standpoint, I mean, you do have to account for that. That is, it's probably only going to be something like an inch or so thick, because remember, the 2 inches goes all the way to the bottom of the although it doesn't indicate that very well. But think, even if it's an inch of concrete and it's only 14 inches wide over the entire bridge, that's not feathers. That's something you have to account for. Does that make sense? Another thing that you're going to have to account for when you do loads is not just the deck and the haunch, but you also have to account for this little triangular overhang taper. You have to account for that too, okay? Because that comes from essentially your overhang brackets that are used to form the deck. You'll usually have something that sticks out about like that and sort of juts into the exterior beam about like that. you'll have stay in place form work here, but when you pour the deck, you can get that little overhang taper. That's additional weight that you have to account for. Does that make sense? We'll talk about more of that stuff though as we get closer to it. Everybody okay so far? Okay. So better than that. Okay. Now, you all by now know the secret weapon of structural engineering. Yeah.
Do you have to account for the equipment load? Like the equipment that's used to pour the concrete, finish it, and all that?
When you're assessing the constructability limit state, like the survival of the bridge during construction, absolutely, yes, you do. The screed rail, the finishing machine, the bid well, all that.
Will that be more than the normal daily loads, or is it less?
Okay. Let me answer that. Let me try and answer that carefully. It's probably not more than the loads, but it could result in higher stresses because remember, think about it like this. Ultimately, when you're looking at design, I mean, moments matter, but my over I to get stresses, that's going to matter a little more. Okay? And what I'm saying is that when you're pouring the wet concrete and placing the deck onto the girders, it's a non-composite girder. So your moment of inertia, is a lot lower. So you see what I mean? Like in its finished state, the moment of inertia is bigger. The loads are bigger, but the moment of inertia is bigger also. So during construction, you might get a worse stress in construction than you do in the finished state. Does that make sense? But to go to your specific question about the equipment, the bid well, the screeding rail, all that, yes, absolutely, you do need to account for it. But not in the finished state, that's only during construction.
So then your girder would need to be what supports all that weight,
No,
not
you're exactly right. Because think, if I have a bridge and I just pour wet concrete, how is it resisting that load? How is it helping with the strength? It's just a puddle of wet concrete. It's just load at that point. Once it cures and it becomes locked with the shear studs, it becomes composite, then it can help. Does that make sense? Else okay with that? Okay. Now, by now, you all know the secret weapon of structural engineering is a samurai sword or a lightsaber if you're a sci-fi fan. Now, this girder is split up. Like, if you look at the girder, you're seeing the same girder, or you're seeing the girder along the spans, but there are different sizes of the girders, like around the pier, than there is in the main body of the span. In other words, this beam right here, or this section, has different flanges and web sizes than this one. The reason for that is because A, the moments and shears are different here than they are there, but B, it's also about different behavior. This is in positive bending, this is smiley face, this is over the pier, this is negative bending, this is frowny face, okay? So because of that, your girder size can change along the span. Now what we're going to do is we're just going to look at section properties along the positive bending region. So I've got a girder that has a top flange that's 14 inches by 3/4 of an inch. I have a web, and my drawing's horrible here on the board, but just bear with me. The web is 42 by 7/16, and then this is 16 by 1 1/4. Everybody okay with that? Okay. Now, so what I'm going to do is I'm going to open up an Excel sheet and let's do some calculations. And I'll probably draw some stuff on the Excel sheet to clarify what we're doing. Okay. So, first thing I want to do is I want to put some sort of dimensions here. So let's do this. Let's say shape. Let's go top flange, web, bottom flange. Okay. And we'll say the width in inches and the thickness in inches. So you all can follow along with me if you want. Okay. Now, so I'm going to start entering in our dimensions. So our top flange, it's a 14-inch wide plate, and it's 3 3/4. So you can do 0.75 or equals 3 divided by 4, whatever you want. It doesn't really matter. 42, and then 7/16. And then your bottom flange is 16 and 1 1/4. Everybody with me on that? Okay, now what I'm going to do is I'm going to highlight these cells and like box them, and here's the reason why. And you all can format this later on however you would like, but I'm doing this because these are inputs. Okay, in other words, these values define the girder, but if I need to change the girder, then those inputs are going to change. Once I change those inputs, all of the other section properties change along with it. So I want the sheet to be robust. In other words, by changing a property, I want it to change the calculation of everything else. Everybody okay with that? Okay. If you are okay with that, then let's start doing some calculations. And I'm going to just increase that to make everything match. All right. So I'm going to start off, I'm going to create a little table down here. So let's do shape. Let's do this again, top flange. Actually, bless you, being lazy. I'm just going to copy that over. And I'm going to create 6 columns. And if you've had me for deformables, you remember this. So we have Y, Y, AY, I naught, D, and I. Let me center that up. Okay. Now A, that's going to be in square inches. Y is going to be in inches. AY is going to be in cubic inches. I not probably should have typed this when I was typing it like all at once. Inches to the 4th. It's been a while, but do you all remember this? Okay, all right. Now, what we're going to do in our calculations is the following, okay? Now, we'll sort of draw over here to sort of explain what I'm doing. So here's our girder, and I've got that drawn at an odd scale, but just bear with me. The first thing that we need to do in computing a moment of inertia, if you all remember correctly, or remember this, is to compute the centroid, right? Remember sum of AY over sum of A, y'all remember that? Okay, and in order to do that, we have to pick a common reference point, so I'm going to pick that as right here. We'll call this the datum. So I'm going to start referencing a bunch of distances from the datum and then use that to compute the centroid. So let's see what we get. All right. So let's start off, let's just start filling in each of these columns. Now the top flange, the web, and the bottom flange, the first column is to compute the area. That's pretty basic. How do I compute the area of each of these? Width times thickness, right? But here's the point. I don't go in and say something like equals 14 times 0.75. I don't do that. What I do is I say equals that cell times that cell. Because if I need to go in and make this 16, I want the table to update accordingly. And I want that to happen throughout the entirety of my calculations throughout this project. Okay? So equals that times that, and you can fill in each of the formulas, or you can just use that little black plus here on the bottom corner and just fill that in. So that times that, and that times that. Everybody okay with that? All right. Down here, what I'm going to do is I'm going to create a sum column, and I'm going to sum these up. Sound good? Everybody okay with that? Excuse me. Okay. Okay. Now let's do the y distances. If you remember, the y distances are the distances from the datum that we've chosen to the individual centroid of each location. So I'm actually going to start at the bottom. How far is it from the bottom of the entire section to the center of that bottom flange? Like how far is it from like right here? Now how'd you get that? So don't type in the number, say equals that divided by 2. You see what I mean? Now, here we go. How far is it from the datum to the of that? Yeah, so half of 42, right? Does that sound about right? About 22 and change? All right, and the last one, how do we get that? There we go. So everybody okay with that? Now, if you're doing a centroid, sum of AY over sum of A, all we do in this column is equals that times that. And then we need to sum that up. Everybody okay with that? Not too bad, right? Okay. Moments of inertia. Anybody remember what the moment of inertia of a rectangle is? BH cubed over 12, okay? But when you do this, you've got to be consistent. So it's the width times the height cubed over 12, okay? So if we're looking at the flanges, the width is the 16 or the 14, and the height is essentially the thickness. But for the web, that's backwards. This is the width, that's the height. Everybody see that? So if we're looking at, let's say the top, or let's say the bottom flange, it's going to be equals that times that cubed divided by 12. So you should get a really small answer. Now, it might seem tempting to say, all right, let's just take this formula and let's just copy it everywhere. The problem is the value that you're getting for the web, because the web you should get a much larger value because you're taking that thickness and multiplying it by 42 cubed. And the reason why is because these are backwards. Should be that and that. So if you get a little note here, that little green triangle that pops up and says, whoa, it's an inconsistent formula, don't worry about it. That's supposed to be that way. Okay? Everybody good? Any questions so far? Oh, just so all you got to do is this: just go into the formula, like click the cell, and then click up here in the formula bar. And when you do that, you'll see the cells highlighted, and you can sort of hover like right over the edges until you get the 4 black arrows like that, and you can literally just move them around. Excel tips and tricks, right? Not too bad, right? Everybody okay with this so far? Okay. What we're going to do in this column over here on the very right is we're going to take the moment of inertias and add to them AD squared. Remember that? I naught plus AD squared and then sum that up. That's our parallel axis theorem. Now, the only thing we have yet to define is our D distances, but there's a really simple way of going about that. Okay, if you look at your image, would you agree that the centroid is probably, the centroid's probably around, oh my goodness. Centroid's probably about somewhere about like that, right? So this distance right here, let's say is y bar. Everybody okay with that? Now, how do you compute y bar? Like, how would we do that? We'd take that and divide it by that, right? Remember that sum of AY over sum of A? Okay, all right. So sum of AY over sum of A will give us the centroid, and it's probably going to be, what is it? Just somebody do that right off the side. See, I'm making y'all do some work. Okay, 17.99. So it's about, let's say, so it's about 18 inches from the bottom of this section to the centroid. Would everybody agree with me on that? Okay. Now let's take this bottom flange y. What is it? That this value right here. This value, this 0.625. Would you agree that what this is saying is it's the distance from the datum to the center of that flange, which is about right here, the center of that flange? Everybody okay with that? Let me ask you a question. You said 17.99? If it's 17.99 from the datum to y bar, and it's 0.625 from the data to this, how far is it from this to y bar? The difference of them, right? See, if it's about 18 inches from here to here, and it's about 0.6 or so inches from here to here, then the difference is how far it is from there to there. Make sense? The d distances are the distance from the centroid of each individual shape to the centroid of the whole thing. Okay? Now, an easy way of doing that is to just take each of these. So if you want to compute these d distances, the easy way of doing that is to take each of these y values and subtract from them the centroid, which is that divided by that. And that's it. Okay? All right. Now you can lock those cells using F4, to get the dollar signs in and drag them down. That's fine. Just if you happen to copy and paste this table over, just make sure that you update that accordingly. I actually don't like using the dollar signs. I end up just actually deleting them. I actually delete them. So there's only 3 formulas. It's not that big of a deal to go through and type them out. Does that make sense? Is everybody okay with that? Okay. Now, does it matter? Do the signs for d distances matter? Like whether or not they're positive or negative? Why? They're going to be squared. It doesn't matter because we're going to take I plus AD squared. So equals I plus A times D squared. And then sum that up. Bam. There's your moment of inertia. Now, why does that value matter? Well, it matters for a number of reasons. Sigma equals my over I. That's I. All right? Deflection. How do you uniformly distributed load? It's 5 WL to the 4th over 384 E I. There's I. Here's the best part of it. Let's say you're going through and you're doing your math and you go, oh man, this girder's too weak. That bottom flange, it's got to be 18 inches. Bam, everything else changes. It updates accordingly. That's why these sheets are so powerful, okay? Honestly, you're probably going to be setting up sheets to do everything in this entire class. Plastic moments, moments of inertia, dead load calcs, live load distribution factors. That's going to be what you do. So, yes. As long as, that's a good question. Let me show you. Let me answer that by showing you something. So this is not formatted properly at all. Okay? This is not formatted properly. I would argue that this is a lot better. Okay? So this is a sheet that I made for a bridge engineering course, and you don't have to format it like this. You can format it however you want, but you can notice everything's pretty clean. It's very nicely formatted. The subscripts are all there. I've got the labels that indicates that that's a non-composite section. This is actually the same girder we were just looking at, and you can see everything's very clearly labeled. If you want to set it up like this, as long as it's very neat and easily formatted when you print, you don't need to do hand calcs on top of that. This is fine. I have no problem with your hand calcs being nothing but Excel. But it can't be something like this. This is like me roughing it out and just printing it out, just to get something out. let me qualify what I just said, though. I'm fine for your alternative report if they're a little rough. For your final report, I want them nice. So. It depends. For this, not really. For like some live load distribution factor stuff, like some stuff that is truly bridge engineering related material, yeah, you do. I expect any engineering student with a bachelor's degree in engineering can compute a moment of inertia. It's like expecting that any civil engineering student could do a sieve analysis, or expecting that any any civil engineering student could do a differential leveling in geomatics. You know what I mean? Some things are inherent. A moment of inertia calc, that's inherent. Live load distribution factors for bridges, I don't expect an undergraduate engineering student to do that. So that's the stuff you definitely want to cite and say, okay, here's the equation, here's where that came from. But don't worry, some of that stuff comes from the bridge code, and I will provide a lot of that stuff to you. The bridge code is about $400 a pop. I'm not making y'all buy that. Don't worry. So, does that answer your question? Everybody else okay with that? All right. Is everybody okay with this? One of the other things that you will see in this spreadsheet that I've developed right here is, and this will make more sense when we get into composite sections, but instead of entering in like effective widths and whatnot, I'm actually having the sheet calculate them. The only input is the deck space, or the girder spacing, the deck overhang, the number of beams. If I've got that, I can compute how wide the total bridge is. If I know the parameters associated with the deck thickness, I can compute everything else. So this is just something to keep in mind. We're not going to do this in here, but just think about it. A little bit more work in the back end to make your spreadsheet do more work for you is usually better. Does that make sense? Like let's put it like this. If you had a choice between simple calculations but a lot of inputs and doing a few more calculations and less inputs, ultimately when you start iterating, it'll be less work on you in the long run. So just something to think about. Make your spreadsheets as versatile as humanly possible. And again, don't treat this format as magic, okay? You do it however you want. So just make sure it's neat. That's all I ask. Okay, everybody okay with this? Okay, so I propose this is the moment of inertia right here. So what I'm going to do, first off, I'm going to erase this stuff so I can actually use this area up here. I am going to do some very minor formatting. So I'm going to take that and put a little bit of heading on it. Maybe bold that up and put a title up here. Now I'm going to title this non-composite or steel only. In other words, the section properties that we were looking at just now are the section properties for just the steel beam by itself. In other words, in its non-composite state. Okay? So I'm heading that right there. Everybody okay with that? Now, before we finish, there's a couple things I'm going to do off to the side. Do you all remember, and we did this in steel design, but do you all remember the concept of a section modulus? Remember, a section modulus is the moment of inertia divided by that extreme fiber distance. Remember, it's the distance from the centroid to the way, way tippy top of the beam, or the way bottom of the beam. Y'all remember that? Okay, section moduli are going to be really important when you compute stresses, because take a moment divided by a section modulus, that's a stress. Okay? Now, this girder is not symmetric. Because of that, there's two section moduli. There's a section modulus to the top of the beam and a section modulus to the bottom of the beam. So if when you apply moment, you will get a different stress on the top flange than you will on the bottom flange. Make sense? So we need to compute those. Okay? So here's how we'll go about them. All right, I'm going to do a little heading right here. We'll say top of steel, and we'll do one over here that says bottom of steel. Okay. Now, first thing that we need for either of these is the moment of inertia, which that's easy. That's just that. Okay. In order to calculate a section modulus, we need an extreme fiber distance. Let's start off with the bottom of the section. How far is it from the centroid to the very, very, very bottom, to right here, to the bottom of the shape? What is that distance? Anybody know the number right offhand? I believe he mentioned it earlier. It was y bar, right? Exactly, because we measured our datum from here, right? So our datum to the centroid, that is the extreme fiber distance. So I propose that for the bottom of the shape, it's y bar. AY over A, right? Does that make sense? Is that going to be the same value over here? No, right? How do I get this one? Like if this is CB, how do I get this one right here, CT? The entire height minus y bar, right? So I propose that you do this. Okay, let me drag this over a little bit. I propose that to get this one, you'd say equals the thickness of that bottom flange plus the height of the web plus the thickness of the top flange minus y bar. Does that make sense? That's not bad, is it? Any questions on that? So your section modulus is that divided by that. Now, let's use a little bit of which flange, if we just look at the beam by itself, which flange is stronger? Let's ignore the numbers. Just look at the diagram. Which flange is stronger, the top flange or the bottom flange? Which one's bigger? Bottom flange, right? The bottom flange is bigger. It also has a bigger section modulus, right? Think about what that means. How do you compute stresses? You take a moment and you divide it by a section modulus, right? Okay, so think about that. A bigger section modulus means lower stresses. Now just think about that. If you take that flange and you beef it up, it's going to result in lower stresses on that flange. Makes sense, right? Everybody okay with that? All right. Now let's do some stuff. Okay. Now, before we move on, because we got a few more section properties we need to compute, I'm going to add some more inputs up here. Okay? Now, I'm going to add an effective flange width. We'll talk about that here in a second, actually, in inches. I'm going to add a structural slab thickness. Hard doing this when it's so dark. I'm going to add a modular ratio. And I'm going to add a haunch. Okay. All right. Now these are inputs, so I'm going to make those yellow. These are going to change. In other words, if I space my beams out a little further, then my flange width changes, and my structural, I could change my structural slab thickness and what have you. But let's take each of these one at a time. All right, and I'm going to go back and forward between this and the PowerPoint to kind of clear up some things. Okay. So first off, let's talk about the modular ratio. Remember, the modular ratio is that value n. That's where we're changing the concrete into an effective lump of steel. Remember that? Now, for most typical reinforced concrete decks, let me see if I have that in here. Okay. For most typical reinforced concrete decks, in order to calculate N, you're taking the modulus of elasticity of steel, dividing it by the modulus of elasticity of concrete. Now, steel's 29,000 KSI, has 29,000 KSI Young's modulus. For concrete, if we compute it for normal weight concrete, so 1820 times the square root of 4, it comes out to about 3,640 KSI. Now, when you divide those two and round to the nearest whole number, for most normal weight, normal strength concretes, your modular ratio comes out to about 8. Okay? So unless otherwise noted, take your modular ratio to be 8. Now, let's be clear. That's for a steel beam and a concrete deck. If it's a concrete beam and a concrete deck, it's not going to be 8. It might be like 1 or 2 or something like that. Okay? So it's just something to keep in mind. Now, that's our modular ratio. Our haunch. Haunch is 2 inches. That was defined. But let's also be clear, okay? The haunch is this dimension. In other words, we need to be clear that this dimension is not the same as that dimension. In our bridge, what's this dimension? I'd say it's 1 1/4. Does that make sense? Just keep that in mind, okay? Just keep that in mind. All right? Now, our structural slab thickness, what's that? 8 inches. Now, the last thing we've got to determine is our effective flange width. And that is going to change dependent upon what girder we are investigating. Now remember, the effective flange width is essentially how much concrete deck we are assuming to be effective for a particular girder. Now I propose if we just split this up using tributary widths, we're going to have different girders with different properties. In other words, would you agree that this, about right there, that's going to be the effective flange width for a typical interior beam? Would you agree with that? Now for an exterior beam, it's going to be something about like that, right? Now I'm going to assume all this little concrete on the overhang, I'm not going to assume that's really effective. It's just sort of there. It's not really helping the strength very much. Now, which beam do you think is stronger, the exterior or the interior? Yeah, stronger, interior. How wide? What is this dimension going to be? 10 feet or 120 inches. Is that going to be 10 feet? No, it's going to be like 8'6", right? So this has less concrete helping it out than this one. Okay, everybody okay with that? If we want, we can go, let's just look at an exterior beam. But let's be clear, you're going to need exterior girder and interior girder section properties. You're going to need to check them both. When in doubt, usually the exterior girder is the one that's going to control. So that's the only one I'm going to deal with. So how wide did we say this is? 8'6", so 8'6". Okay. So here, I will say, excuse me, goodness, 8 times 12 plus 6. So it's 102 inches wide. Does that make sense? Everybody okay with that? I'm also going to do this. I'm going to take this small, oh, not that far. But I'm going to do that just so you can see, like, these are dimensions, but that one's a number. So, see, the reason why I'm bringing all this up is if you look at my spreadsheet that I built, like you can see non-composite properties, but you can see short-term composite interior girder, short-term composite exterior girder, long-term composite interior. Everybody see that? So there's 4 different composite sections that you'll need to consider in positive bending. A short-term interior, a short-term exterior, a long-term interior, a long-term exterior. What's the difference? Remember that. Remember we have that short-term and that long-term composite shape. Does that make sense? So let's do this. Let's sort of work this out. So what I'm going to do is I'm going to do an entirely new set of structural calcs. So for this, we'll keep it simple. Let's do the short-term composite section. Okay, short-term composite section. So we'll do a whole new set of calcs. And I don't know, I'll use a different color. We'll make that orange or something. Okay. Now, would you agree that the short-term composite section is probably going to look a little something like this? How many individual shapes are in this composite section? 4, right? I argue no. I argue that there's only 2 shapes that we need to consider. The girder and the slab. Because we just computed the properties of the girder. We just did it. Watch this. So the girder and the slab. What is the area of the girder? It's that. What is the centroid of the girder? It's that divided by that. What is AY? It's that times that. What is the I naught for the girder? What is that? It's that value. See what I mean? Be lazy. I'm lazy. There's no reason to repeat all those calcs. They're all right here. Make sense? All right. We're also going to need to sum these up. So this is where Excel's awesome, because once you get it formatted once, you can just copy and paste. So we'll drag that down one, and we'll copy and paste. Everybody okay with that? And it's pretty nifty. Like once you get your tables and whatnot set up, you'd be surprised how a lot of it's already done for you. For instance, like take this cell. I don't care what's going on. How do I compute what's in that cell right there? I take that times that, right? Just go ahead and do it. Just do it. All right. All right. How do you compute this D value, right? You take Y minus that over that, right? That's the same thing we did up here. It's no different. How do we compute this one? We take Y minus that over that. Okay? Now everything's 0, or these values here. That's going to change when we fill in everything else. All right? How do you compute I? Well, it's I naught plus A times D squared. Sound good? Everybody okay? Is this making sense? Now the reason why I'm getting the same value here that I did up there because I haven't entered any properties associated with the deck. So, sound good? It's 9:50. I just realized that. Time flies. I guess we will get back to this on Wednesday. So I'm going to leave this up for a second if there's anything you all want to copy down. But that's all I've got. And we are not meeting on Monday because of our glorious 3-day weekend coming up. So with that, you all have a wonderful 3-day weekend. For the rain. Nah. Y'all have a great weekend and whatnot. We will see you when you get back. So that's all I got.